Thank you for inviting me to be here. And I'm going to be talking today about the work that we are doing in Google Research in Switzerland in the Zurich office. This is joint work with Thomas Hoffman, who is the Engineering and Research Director there, and with the people of my team, Masi, Katia, Yanis, Yasmin, Evangelos, and Janif, and also with Fernando Pereira, who is Research Director in the Mountain View office. I'll be touching several different things in this presentation, including the knowledge graph that Google recently announced, and some semantic analysis and document summarization techniques. So this is the agenda for the talk. I'll start with some introduction about the vision of our team. Then I'll talk about the knowledge graph from Google. I'll talk a little bit about entity-driven information extraction from the web. And finally, how to put all these things together into a single application. So, our team, we are working on natural language understanding. We have recently refocused ourselves a bit more into tackling text summarization problems where summarization techniques can be useful, but summarization in a very broad sense. A traditional definition of text summarization is this one provided by Manny and Maybury more than 10 years ago, distilling the most important information from a text to produce an abridged version for a particular task and user. In our case, we call it text summarization as long as the source is any document in any format. It can be textual, not textual. And we don't put any restrictions of the user either, so it can be for human consumption or for machine consumption, as long as the task is finding the most relevant information in your data source. So this is, as you can see, it's a very generic definition that can include many other traditional NLP problems. Regarding the field, most reported summarization work reports intrinsic evaluations, and these intrinsic evaluations usually are focused on the content of the summaries, on informativeness. The typical metrics that are used are push or basic elements, all of which are focused on the informativeness of the summary. So they want to make sure that the summary contains the most relevant information. And even human analysis, usually people rate summaries across different dimensions, including readability and informativeness, responsiveness, but then usually systems are ranked only regarding informativeness and responsiveness. And there is very little then on extrinsic summaries, extrinsic evaluation. For a particular task, how useful is this summary? And on the other hand, there are many different applications of summarization, from web search snippets, automatic generation of biographies, Wikipedia pages, news summarization for small screens like mobile reading, email summarization, open-ended question answering. So the question is, if we have all these different applications, and they're quite different in nature, why shouldn't we be focusing on extrinsic evaluations for all of them? Then there is another distinction that we can make in the field. One is that as people have been focused on evaluating summaries on informativeness, they have been focusing a lot on selecting what to say from the original documents, on content selection. And until very recently, this was mostly extractive approaches based on sentence scoring. You have a set of original documents, and you rank the sentences, and you find a subset of sentences that contain the most relevant information from your original data set. But there is not so much research on how to say it. There is some work that I mentioned here on sentence compression, given a sentence how to make a shorter version of the sentence, sentence fusion, given a couple of sentences that you want to put in the summary, how to merge them into a single one, text simplification, compression and paraphrasing grammars. All of these things could be roughly grouped together into text-to-text translation. And then finally, there are very few works on discourse planning on natural language generation for summarization, but not really much of it. So, how is our approach to the field? We want to focus on diverse applications of this technology with a very application-driven team, and we want to push the state of the art in text summarization in a very application-driven way. So, as there are many unexplored applications of extractive systems, and there are many systems that are already in production, like I mentioned before, web search snippets, where there are still improvements that can be done. So, the plan is to start with the low-hanging fruits, with the very engineering problems where we can make quick progress, but at the same time, our vision is that summarization is a complete problem, similar to machine translation and many other NLP tasks, where to do it perfectly, we need full language understanding. So we expect to be finding across the way all of the other core NLP problems, from parsing to name entity recognition, entity disambiguation, and so on. So on the way, we'll be integrating with existing semantic analysis tools, and slowly the plan is to move towards abstraction, using entity disambiguation, relation extraction, and supervised semantic parsing, and many other semantic technologies. So this talk is intended to showcase an application that we built in the first quarter of this year. This application is mostly thought to showcase how text summarization can be used in the web using semantic analysis technologies and grounded on the Google Knowledge Graph. So we can move on now to the second part of the talk, the Google Knowledge Graph. What's the Knowledge Graph? Traditionally, in information retrieval, we were focusing on matching text strings, including synonyms, misspelled queries, and many other different scoring techniques to be able to match the query with the documents to bridge these lexical gaps between the vocabulary of the user in the queries and the vocabulary used in the documents, and to find the most relevant documents for the users. So you can see that, like in this example, you can see that the query is misspelled, so it's automatically corrected. Documents may contain synonyms of the query, that may contain other related words. The query may be very long, and you may need to optionalize terms. So all this kind of term-based information retrieval was the core part of the retrieval system. But we don't always know what you mean, and sometimes it's useful to really understand what the user means with the query. Like in this example, if you have a query which is Chelsea and you don't have any other context, the user might mean the football club and might be interested in the outcome of the latest matches, might be interested in generic information about the club, but maybe the user is looking for local information about the area, Chelsea in London, or maybe looking for TV series, movies, any other kind of information related to all the different entities in the real world whose name is Chelsea. So the goal of the knowledge graph is to take all the real world entities, and not only real world, also imagined entities like movie characters or book characters. Take all these things that exist in the world and map all of them into a single repository. So all these entities, all these real world entities will have unique identifiers, will have metadata about them, we may have pictures, they will be grouped together in classes, and we will know relationships and attributes for them. And how can we start building this? There are many structured data sources already available that contain a lot of information that can be a good starting point. And on top of that, we also have the web, and we have a lot of information on the web. So the task here to build a knowledge graph was to align all these resources, to put them all together into a single database of real-world entities. Just to mention some examples, Wikipedia, you all know, has, in English, it has more than 4 million entries already, so there are 4 million entities that we can straight away use from Wikipedia. Freebase It's a superset of Wikipedia that contains as well structured information. It's owned by Google, but all the information of Freebase is available on a Creative Commons license, so it's freely available for either research or commercial purposes. And it's also a collaborative effort similar to Wikipedia. So it has all the Wikipedia entries, and then it has attributes of the entries, it has relationships between the entries, it's based on a very formal schema defining the knowledge base, on top of which it's possible to do inference, for example. Some other examples, we have the shopping dataset, which is the dataset of products that are provided by the product vendors and producers for Google Shopping, for the product search application. In Google Local, we have all the geographical databases that are used to power the local search of Google. There is also some other data sources like the CII Factbook. Google Books also contains hundreds of millions of books, data obtained from publishers, and finally there are some research works on extracting data from the web, like I can mention web tables here from Michael Caffarella, where structured information can be learned from tables or other semi-structured resources on the web. So once all of this has been put together over the past 2 years at Google, and a database has been created with 500 million people, places, and things, and 3.5 billion defining attributes and connections. So once we have this available, what can be done with this dataset? If we think, for example, for the web search application, a very simple thing that can be done is whenever a user query is ambiguous, and it can mean several things, we can provide the option of the user to refine to see results about the exact thing that the user is looking for information. Like if the user is looking for Notting Hill, the most salient meanings of this query would be the movie with that title or the region in London. So we can offer the 2 meanings there, and the user can select one of them and see only results related to that meaning. It's also possible, sometimes, if we have a query like Darwin, sometimes we can also guess that the user is most likely looking for some of the meanings. So we can straight away highlight information about that meaning, like in this case Charles Darwin. But there will still be other meanings that will be useful for other users, like the city of Darwin in Australia. So we can also mention them at the bottom and allow the user to refine the query to take that one. So, and then aside from that, from specifying the meaning of the query explicitly, it's also, we can also straight away provide some results, some relevant information that is useful for the user and might provide immediately the answers that the user is looking for without the need to do research themselves. So for example, for a query like Shakespeare, we can show already a summary of the entity. We can show an image, a small description of the entity, and some relevant attributes. In this case, birth date, death date, and it's relevant about them, it's relevant the plays that Shakespeare wrote, and also for users it's usually relevant movies that are based on these plays. So all this information, we make them available straight away. And this information will be different for different users, for different queries, for different entities. So if you have a user looking for a Lynn Collins, the astronaut, the American astronaut, relevant attributes for this entity will be the time spent in space or the space missions where she participated. Whereas if you're looking for a singer or a group, relevant information for the users will be when this group is singing nearby the user in the future, and songs that were released by this user that were popular. And so all these attributes, everything, there is no manual work in here at all. So everything is ranked and selected based on aggregated user behavior, understanding what users usually are looking for when they enter these queries. Some other applications of this is to be able to identify entities that are related to other entity and understand why they are related and provide this information to the users. So if the user has searched for the Buckingham Palace, we can show related places, related touristic places to visit close to it. And the user can navigate from one to the other. A user can move in a broader way from one painter to other related painters. And something that we provide also is the possibility of the users to give us explicit feedback about the data at its source. Once an application like this is offered to the users, you always have implicit feedback from them. So if you show information about related entities, for example, and you see which are the related entities that the users click the most, you have feedback about what they are finding more interesting and more useful for them in the list of related entities at the bottom. But then, at the same time as we have this implicit feedback and we can use it to improve the system over time, it's also good to give the possibility of providing explicit feedback that we can feedback straight away into the knowledge base. Now, there are many other applications that can be used. So you were seeing question answering in the previous talk, and Hans, you were asking about more traditional question answering. So for very typical factual questions, we can provide the answer straight away. So right now, if you ask something like who is the CEO of Google in natural language, or also Google CEO as a single bag of terms query, we provide straight away the answer. That the answer would be Larry Page, and you can see the knowledge panel at the right hand side. Or you can ask who is the CEO of Yahoo, and you see Marisa Mayer. You can also ask for categories. So you can ask for things like Harry Potter movies, and you see all the movies listed there at the top. So you can browse through them one by one. You can ask, and we can also do some inferences on the knowledge graph, requiring several steps across it. So maybe you know the Bacon number that is defined as the number of people act together in the same movies. So you can consider that, so the Bacon number is defined recursively as, for Bacon the number is 0. If a person acted in the same movie with Kevin Bacon, then they have a Bacon movie of 1, and then the recursion comes if you acted in a movie with some other people, the minimum Bacon number of those other people plus 1 would be your Bacon number. And this was inspired by similar numbers defined in mathematics. So you can ask for things like a Stephen Hawking Bacon number, and then you need to go to the knowledge graph and to see how many loops you need to go into this relation of acting in the same movie together until you reach Kevin Bacon in the graph. So these are the kind of things that can be where we can give straight away questions. So what's the future we could expect in this direction? The plan is to evolve the technology, and hopefully in the future we'll be able to help you by answering harder and harder questions, requiring more inference and more semantic analysis. Things like, where can I attend a YouTube concert in warm outdoor weather? Or where can I find an amusement park with a vegetarian restaurant nearby? How many governors were born in a different state that they govern? Or what is the coldest lake in the world in July? These kind of questions are kind of questions that we expect the knowledge graph to be able to provide an answer sometime in the future. But then, going back to our research team, most knowledge graph data contains static objective data. So you can go there to find a repository of real-world entities. You can get information of these entities. You can ask what propositions are true for these entities right now. Which is the parent of this person, or what are the siblings? Or you have also temporal information encoded there, so you could ask what was true about some entity 1 year ago, what was the president of this country 4 years ago. all this information is inside there. But there are many user information requests that are about dynamic and subjective data that it's much harder to encode in a knowledge base like this. Questions like what is happening right now in Syria, how did the situation evolve up to the current point, how are different people or different organizations reacting, what are the main opinions about these events, what are the established opinion makers like mass media reporting about them in different countries, in different languages, what are opinions from web users about it, and how can I make sure that they have considered all viewpoints in a question like this. So these are the kind of questions where we think that taking many different unstructured sources and putting them together, aggregating and summarizing the information should be a very compelling use case. So with this, I'm moving forward to the third part of the talk, entity-driven information extraction. So how is entity disambiguation on the web usually done? Most systems for entity disambiguation, also called entity linking, they're very similar in nature. I'm going to highlight this work Hofart 2011 from Gerhard Weikum's group in MPI, but this generic architecture is followed by many other teams working on the same problem. So in general, when you have any text document, or you will have the whole web, and you want to identify any possible mentions of any entity in your knowledge graph in that document, and you want to identify and disambiguate all mentions of all entities. So then the first step will be that for every entity, you will know different ways of referring to that entity that you will have collected beforehand in your knowledge base. So you may know that Bush, this unigram, may refer to George W.H. Bush, or may refer to George W. Bush, or may refer to the music band Bush. And there are probably hundreds of other people in the world whose surname is Bush. So you will have all these entities as possible entities to which this mention refers. So Google recently released a data set of entity mentions collected from the web from anchor texts pointing to Wikipedia. So that's one possible source from which this set of mentions can be obtained. So, and same for many other things. So Operation Desert Storm, that's one mention, a trigram that probably has only one interpretation in the whole knowledge space, Operation Desert Storm. And you may have other terms like president, who may refer to just the title president, or might also be a mention of entities who are presidents of different organizations. So you collect all these mentions, and then you go to your knowledge graph, and you load all known relations between all the possible entities that might be mentioned in this document. And with this, you generate a knowledge graph specifically for this document. Every possible entity that might potentially appear in the document, and all the other entities that are related to that one. And finally, you do joint inference to disambiguate the reference. You find the mentions that are most likely given your prior for dimensions, because some mentions are beforehand more likely to appear on the web in general than other possible entities. But then taking into account all the context and all the other possible mentions that might be co-occurring with them, you find the set of entity assignments that maximizes the joint probability of the whole assignment in the document. So I'll mention here this work done by Jasmine Altum and Masi Charamita. They started from the system from Gerhard Weikum's team, and they extended it. They started to compare with this method. They produced a machine learning classifier using a local model. So for every possible mention, having a local model of local features that mention for example, syntactic features, what it is used in the sentence, or some contextual features, what other words appear around it. And with that, they train a logistic regression classifier to rank all the possible mention candidates, and just this local model without using any global information from the document, just looking at every mention in isolation and disambiguating every mention in isolation, produced comparable F-score performance with this other system. And they did the second step using a global topic model to rank the candidates, taking into account the global ranked list of mentioned candidates in the whole document, and using the global model, they produced some nice improvements into both precision and recall over this local model. So this is just an example I wanted to highlight. There is much other work on entity disambiguation. But the conclusion I want to bring from this section is that there is actually a virtuous circle here. The more data we have in the knowledge graph about all the real world entities, the more accurate the disambiguation is, because we have more information to be able to perform this joint inference more precisely. And at the same time, the better disambiguation we have, the more confident we will be about the decisions we make in disambiguating, and the higher our recall will be, and the more we can learn from the web about all these entities to extend automatically the knowledge base. Okay, so with this I go into the final part of the talk. So I want to highlight here how all these different parts can be put together into a single application. So we started from the question, we know there are many different applications of summarization, and we are working on them. But how to put everything together, and how to summarize the web in the context of the knowledge graph. We have all this information about all the real world entities, and we have all the web. How can we make web summaries for these entities? And the approach that we've taken here is to separate what is talked about an entity from what is talked about that will be an entity in the knowledge base, and to separate that from what is said, the propositional information that is stated about this entity. So in a few steps, the approach that we followed to generate web summaries of entities was the following. First of all, annotate all the web with references to the known set of things, to all the entities in the knowledge graph, using the entity disambiguation techniques that I was talking about before. And you have to take into account here that we have this closed set of possible entities that we're interested in. In this case, we have this knowledge graph of 500 million entities. That's the closed set of entities, and if something is not in the knowledge graph, we are not going to be able to annotate that. And this is in contrast with the area of open information extraction that has also received a lot of attention and a lot of work recently, where they try to extract information having no knowledge base, no reference knowledge base behind. We assume we have the knowledge base, and we try to match only the things that we have in the knowledge base. Once all the web has been annotated with all these references, we create an entity index of the web, an inverted index saying for every entity what are all the web pages that mention this entity. Next, we cluster all the entity mentions around common events affecting these entities based on the propositional content available in the documents. So we want to identify all the documents in which people are talking about a certain entity regarding some particular event that has happened. And finally, we do entity-centric summarization and aggregation of what we have found. So this first step, that is the prototype that we built in the first quarter of this year, we decided to follow a very engineering approach here, so there is no really research breakthroughs. But we put the system together in the following way. We assume that events influence what the web says about entities. And temporality is important. Usually people, when they define entities, they relate them to events, and events are usually anchored in time. So they may have happened in a given time or in a given time interval, but usually these events have some time in which they were happening. So we use this temporality as an organizing principle. And what we do is, given an entity and a time interval, we provide a summary of the most memorable events involving these entities. And the strongman system that we built was the following. First of all, we find and cluster the most relevant news involving an entity. We filter and rank these clusters in order of importance in the time interval that the user has requested. And then we concisely summarize each news cluster, and we visualize these summaries in temporal order. For something like this, if you want to know a timeline of what are the most relevant events involving this entity over time, with web search it's really hard to have the answer straight away. You will need to do some research yourself with different queries and going through the results. If you try just a query like REM, there are many issues. On the one hand, if you want recent results, for example, you want all the events in the past year, you can use the tool at the left to restrict to the past year, but then you will get another set of results where you may also get confusion around entities, because REM may refer to the music band, or it may be a first name of a person, or it may refer to the rapid eye movement stage during sleep. And then even with a little help, writing the query in an unambiguous way and using all the tools at the left, it's still a little bit hard to find a timeline like that. So these are some screenshots of what we built. We want to have this entity-centric view on news. So you search for an entity, and you get a summary of important events that have happened to the entity in the time interval that you have decided. So one important part here to begin with is how to allow the user to query for a given entity. And for that we are using the freebie suggest widgets, where you can write a query and you automatically get suggestions of entities that you might be referring to with that query, and you can select exactly the entity that you are interested in. So to give you some examples, if you search for something pretty unambiguous like Angela Merkel, you get it as the first result, but you can also get some other entities that are related to that. And if you search for a more ambiguous query like a proper name like Jim Jarmusch, there are actually several people or books or musical recordings, TV episodes, movies that are related to this person. So the user can select exactly the meaning that they want, and then there will be this timeline of important events involving this entity. Some more things we do, for each of these events we select a title defining the event. In this case, for a query like Fernando Alonso, we can get a title like Fernando Alonso roars from 11th to win phenomenal race, and then we also provide a small summary of what happened there. So just in this example, it's explaining that he has now a 20-point lead, that he told his fans that this was the best in his 29-win career, and some background about what happened during the race. This is just another example. You search for Johnny Depp, you get information like his divorce and some other events. In particular, here you see highlighted that he released this Dark Shadows movie in May, and you see also some summary of information related to that event, to that movie release. So how we do each of these steps? For news selection, we restrict to the Google News corpus. We reuse a lot of data and ranking signals from Google News whenever possible, but we also have to add our own ranking signals based on entities to identify when a news is really important. When an entity is just mentioned in the news because it happened to be to play a minor role in the event, or when the event is really central about this entity. So basically, we want to find events that are really changing the entity, that are really defining of the entity, and could appear in a definition document about the entity. And once we have all these news clustered together into sets, and with quality, with relevant signals available globally and about different entities, given the entity provided by the user, we score all the news clusters based on many features. Features like the global relevance of the cluster, the topicality of the entity in the news documents, that it really has to play a central role, the prominence of the entity in the cluster with signals like, for example, the percentage of titles in that news collection that are explicitly mentioned in the entity, and the typical ranking signals for web search, freshness, non-redundancy, and so on. Once we have selected the news we want to give back to the user, we summarize this news. And the current summarizer is a traditional extractive multi-document summarizer. In particular here we use the entity to guide the summary, so it's not a generic summary of the event, but it's really highlighting how the entity played a role in that event. For headline selection, it has some specific tweaks to be able to find a one-sentence summary from the one-sentence documents of all the possible titles that we find in the web. And here in particular, so some additional requirements we said is that the title has to be objective, has to really describe what happened in the event, so we don't want catchy, creative titles that are written by journalists to catch the attention of the reader, but are not really a good description of what happened. And finally, for the news description, we use full document summarization. With these summarizers, we get the state-of-the-art results on academic corpora. We have also very good results on the task-specific evaluations that we do. And some other work from Katia Filipova I wanted to mention as well is sentence compression. This is especially relevant for title selection, because sometimes in a news cluster the titles are all of them either too long or too creative, and it's hard. Yeah, if two persons have married, we want the title to be X and Y are married, X and Y are married. We don't want to produce a 20-word title, X and Y tied the knot in this place, and so on. So for this, one of the technologies we use is sentence compression. So the definition of the task is that if you have a long sentence like this one in the slide, we have a system that you can give a target character length or word length. This system is very much syntax driven, so we take the dependency analysis of the sentence, the dependency graph, and then it removes the constituents that it believes are less relevant in the context where we want to show the sentence. So for example, for this sentence, you can see that the temporal modifier on Thursday was removed, the title of the person US humanitarian chief was removed, and finally you get a shorter version of the sentence. Valeria Moss said that she was devastated by the destruction she saw in Baba Ammar district of the Syrian city of Homs, and she wants to know what happened there. So this is a shorter version of the sentence that contains mostly the most important information in the sentence. But you can also be more aggressive, and you can specify a shorter limit, and then the output of the system would be a shorter version of the sentence. Valeria Moss said she was devastated by the destruction she saw, and she wants to know what happened there. And you can be even more aggressive and say a much shorter target limit, And then you just get, she was devastated and wanted to know what happened there. So, so this is a prototype we built. What are we planning to do in the future? So we want to do some more serious event detection and extraction. There is still we built all the basic infrastructure. We have done all the basic engineering work right now, but there is a lot that can be done to improve the quality of the system. And in particular, we are working into relation annotation and event annotations from the different news data sets. We want to really understand what the news are reporting about a single event, to understand what happened there in a structured way, to link that into the knowledge graph. And then, once we have all this in a structured format, we want to explore different abstraction-based event headline generation techniques. So we don't have to rely on a headline written by a journalist, but we can really understand what has happened here, and we can construct our own headlines of what has happened in a particular event. We want to include user-generated content. This is a very big fraction of the web that is written by web users, and it gives a good understanding of what are people's attitudes to the different events that have happened and the main divisions of opinion. So we want to include user-generated content into this by mapping people's opinions to events in news stories, and to make all this available as well, and to put all this together, developing a full-blown timeline view where you can identify what are the events the most important events involving this entity, and you may be interested in one event and you want to say what is the background of this event, this particular event, and explore the different news stories in many ways, going broader, going deeper, and finding the different interpretations of the events, and helping all the users to make their own opinion of things that have happened. So thank you for your attention, and we have some time for questions now.
Okay, there's enough time for questions and comments. My name is Martin Sidorf, and I'm doing a research on entity summarization on knowledge graphs, so this is very close to what you said. And my question is if it is possible to use some part of the data Google has.
All the freebase data is public. That's 20 million entities. So you can download it and use it. And it already contains the head of the distribution. So the most relevant entities that you're going to find in the documents, they are all in freebase.
Hi, my name is Christopher Darosh. I was a question, do you use collaborative filtering when making the order of entities in web search?
For the order of entities, so most of it is based on user behavior on web search. So to decide which entities to show, or to decide the order of the entities. So if you have a query like Darwin that they put as an example, and it has two interpretations, Charles Darwin and the city of Darwin. Something that we know is that most users end up going to web pages that are talking about Charles Darwin, and then you have less users that are interested on the city for a query like that. So you can use that information to prioritize to rank the entities and put the one that most users are interested on the top.
Is your project English language focused?
That's a good question. Most of this work starts in English because that's the biggest market on the web and what most people in the world understand. But we don't use any almost any language-specific techniques. So most of what we do can be adapted to other languages, but
techniques or tools?
techniques. But so most of the things we do can be adapted to these other languages. So for example, I mentioned parsing here. We use the parsers developed by Slav Petrov and Ryan McDonald and Keith Hall in New York. They have been working a lot on producing a common tag set for part of speech tagging and for dependency labels for all the languages in the world. So it's a very generic tag set, but it can still be quite useful, and it makes it very easy later on. Once you have your system tuned for English and with good quality and you want to internationalize it to other languages, having these resources make it very easy later to internationalize them. But having said that, it also requires some work on making sure that the quality is good enough. And so for example, the knowledge graph in web search, it's only launched in English right now. The first launch was in English in the US only. Then there was a second launch including all the English-speaking world, the UK, Australia, and so on. So I hope to see international versions of that at some time. But as you can imagine, there is all these things require time to make sure that the quality is good, even if you are not using any language-dependent techniques. So for the work we do is the same. We start working in English, but once the system is well, it will take some time until it can be ported fully with the same level of quality into other languages and locales.
What about integration between languages? For example, when I search for a Polish person and the results, the relevant results would be in both Polish and English, and with a system which depends on a language, would it lose the ability to provide for timelines, for example, of events?
For timelines. So for example, in Google
headlines
News,
in both Polish and English, at the same page.
So right now in Google News, if you search, if you're using the US edition of Google News and you search for a foreign entity for which something has happened, usually for every cluster we try to show some foreign language article as well, because usually they provide a different point of view. So if something is happening in China right now and you search for it, you will see the cluster of news. And you should see saying in China, and you see some title of an article from a Chinese newspaper that you can click there and you can see the Google translation of that article into your language. So that's something that we think is very relevant, because in particular for news, in different languages and from different countries you are going to see different points of view. And this is very important for people not to really stay with what is reported in one place, but to know all the different points of view and to make their own opinion. So that's something we definitely want to do.
Yeah, hi. My question would be, do you have any publicly available visualization of this graph, so the way you interconnect the content, or if not, do you plan on having one?
I don't think we have one, and I don't know of any plans to do so. Yes.
An engineering question. So in the past, Google has made great contributions to storing and managing big data for this. Nowadays, there's big table implementations which are even open source. So I was wondering, the Google Knowledge Graph, is there a real graph database behind that? So do you have your own graph database, or how do you store the graph data?
So it's stored internally in Google. We don't explain how we store it, but what we make public is an API. There is a query language called MQA, and through this API with this query language, you can send queries regarding the graph. So you can ask queries saying, tell me all the like questions that I mentioned here, like all the governors of US states that were born in a different state. That's a query that you can right now send through the Freebase API using this MQA.
Yeah, I thought this was a very general question. This is a big table implementation of graph database, but I understand you can't tell us now.
Right.
I have a question concerning the size of this knowledge base. as a knowledge graph. On the one hand, with 20 millions of entries, as you've said, it's a big one, and I wonder who created a thing like this. Was it done half automatically or human-made? Or and the other thing is that 20 millions of entities compared to a 7 billion population of humans on our planet is a small portion of them. And the other question is how this entity graph is going to be developed, extended, what frontiers are or limits.
Okay. So the first question is the 20 million entities, how was the graph constructed? This work was started by a company called MetaWeb that was acquired by Google, I think it was 2 years ago. And they started importing information from Wikipedia and from other sources like Wikipedia. And then they made all this information available, and they also provided a web interface for any user to collaboratively add more information, correct information entered by other users. So it was mostly a user collaborative effort, and it continues like that. It also has an API where you can do bulk imports of data, so you can add straight away, if you have 10,000 entities that you want to add in a given batch, you can send all the set of entities, or if you have relations or attributes, you can send a very big data set. It has a very strong quality evaluation for the data that is added, because Freebase makes the guarantee that the data that is there will be 99% accurate. Because it's a collaborative effort, you cannot guarantee 100%, but it employs a lot of resources in making sure that the data that is entered complies with this quality requirement. But it's mostly a collaborative effort with this quality layer added on top of it. And then you were asking also, there are 7 billion people in the world. We have 500 million entities in the Google Knowledge Graph, so what are the plans to extend it? So the plan for the knowledge graph is for now, is to contain public information. So information that you can find in news, in documents on the web. So that's why we have books, because any book that was published is public. Same with products, we have places. All this is public information. And then regarding people, we have people that are valued also. People that are reported in the news, people that appear on the web with enough information. It's not our objective to have a knowledge graph with all the 7 billion people in the world. So there are